we left off, last class we were just starting to get into kinetic molecular theory, and I've been talking about kinetic molecular theory kind of as we were going through, especially the simple gas laws. We're going to take a more explicit look at what kinetic molecular theory talks about and informs us about for those gas laws. So for Boyle's law was our P1V1 equals P2V2. And so this states that the volume of a gas is inversely proportional to the pressure. So if pressure goes up, volume goes down. If volume goes up, pressure goes down. Basically, if you squeeze something, the pressure is going to increase. And if you allow it to relax and expand out to where it would normally be, the pressure will go down. And kinetic molecular theory are thinking about our gases as little ideal spheres that take up no space and just collide off of each other. Lets us know that decreasing the volume would force the molecules into a smaller space. If we're squeezing down, if we're decreasing the volume, all of our particles now have to cram into a smaller amount of space, and so they're going to collide more with each other. So this is going to increase collisions. Decreasing volume increases collisions, and increasing collisions will cause an increase in pressure. Since collisions of the gas particles with the walls of the container are what cause pressure. So decreasing our volume increases our collisions and also increases the pressure. And then the opposite is also true. If we expand the volume, if they've got more space where they can spread out, then they're going to have a longer time before they run into stuff, and so they're going to cause less collisions. We also have Charles' law. Charles' law tells us that the volume of a gas is directly proportional to the absolute temperature. You might also know it as V1 over T1 equals V2 over T2. So with kinetic molecular theory, when we increase the temperature of the gas, the average speed increases. So increasing temperature increases speed/velocity. So our particles are moving faster, so it takes them less time to run into stuff. So we get more collisions. And since in Charles' law our pressure is constant, to keep the pressure the same, we have to expand the volume, since expanding the volume decreases the pressure. So that's kind of our equilibrating force. We also increase the average kinetic energy of the particles. And since the kinetic energy of our particles increases, they're colliding with more force. So it's not only more collisions, but they're also more powerful collisions, which causes our volume to expand. So more collisions and more forceful collisions. So our volume increases or expands to maintain constant pressure. For Avogadro's law relates N and V. The law of the volume of a gas is directly proportional to the number of gas molecules. So N over V for one state is the same as N over V for another state. And this was our law that says that when we blow gas into a balloon, for example, or a ball or a tire, as we add gas particles, in the case of a balloon, it's going to inflate because its volume can expand. In other situations, if the volume can't expand, then we would expect an increase in pressure. Basically, more particles, because we're adding gas, we're adding moles or numbers of particles. More particles means more collisions. So if we're increasing the amount of gas that we have in our container, then we're going to have more collisions. But because pressure is held constant, like with blowing up a balloon, pressure inside the balloon is the same as outside the balloon. So the pressure is going to cause the balloon to expand to maintain constant pressure. So the volume increases. So more particles means more collisions, means more pressure, but that pressure turns into increased volume. And I think I talked about most of these when we were covering the simple gas laws, but this is just showing that our kinetic molecular theory explains them, since we just talked about KMT. Kinetic molecular theory also explains Dalton's law of partial pressures. So remember that in kinetic molecular theory, the identity of our particles does not matter. So all particles behave equally. So particle identity does not matter. So under kinetic molecular theory, in our ideal gas situation, our gas, if it's helium or if it's some really large thing, like if we have like gaseous sugar molecules or something crazy, those are going to behave exactly the same, even though they're very different particles. They don't take up any space. The particles are going to have this negligible size. They're not going to have any interactions. And so all the particles should behave the same, and so we can just add the partial pressures up. Partial pressure sum to total pressure. It's the PTOT P sub A plus P sub B, and so on and so forth. That's our law of partial pressures. And even if our particles do have different masses, they're going to have the same average kinetic energy at a given temperature, since their kinetic energy is based on temperature. They might be moving slower if they're heavier. They might be moving faster if they're lighter, but they're going to have the same average kinetic energy. And so the total pressure of the collisions is going to be the same, since the pressure is based on the force of the collision, which is based on the kinetic energy. You can think of this as like if you've got a really small person fighting a really big person, and the really small person has like lightning fast hands, right? They're hitting, their fists are moving really fast, but they're really light, so they don't have a lot of weight behind their punch. The big person is going to be moving more slowly, but because they're a bigger body, they've got more weight to put behind their punches, and so they're going to hurt more. So kinetic molecular theory implies PV equals nRT. You can see the textbook if you want to see where that comes from. You don't need to know where it comes from. And its behavior predicts behavior that's consistent with our observations and measurements of gases. So it mostly tracks with what we see and experience in terms of gases. It does break down under some situations, but for the most part, it's a fairly accurate representation of how gases behave. And it's like good enough for most applications that we'll encounter. When you get to higher level physics and chemistry, it doesn't work, and we're going to actually learn about some of the ways that it doesn't work as well. So now we're going to get into some fun math stuff. Fun potentially having quotation marks around it, depending on how you feel about it. Okay, so average kinetic energy of a gas molecule is related to the mass and the average velocity. So these are some average values. Our kinetic energy, this is true for any individual particle, but we're going to have a range of different velocities, and so we're talking about these just generally as averages. Our kinetic energy, Ke, is equal to 1/2 m, where m is mass, times v, which is velocity, and the velocity there is squared. Our kinetic energy is going to have units of joules. Our mass we would typically represent as units of kilograms. And velocity, v, is going to be meters per second, which is squared, so meters per second squared. Meters squared per second squared. I'm only pointing that out because we'll see that come back again later with a different equation. So if our gas particles have different masses, the only way for them to have the same kinetic energy is to have different average velocities. So, for example, if mass is small, velocity must be higher to have the same kinetic energy. Maybe another related analogy would be cars. If you've driven a small car, if you've driven a big car, or if you've been in a large vehicle or a small vehicle, or if you've just been on a highway, semi-trucks tend to accelerate really slowly because they have so much more mass than, for example, like a little Mazda Miata, which is going to be a really small car, like a small sports car sedan. So the small car can accelerate a lot more quickly, even if they're putting out the same amount of energy. The semi-truck is just so much bigger, it's going to take way more energy for it to get going, so they typically tend to accelerate and decelerate more slowly. It's the same for gas particles, just on a much smaller scale. So if in a gas at a given temperature, the light particles have to travel faster on average than heavier ones for them to have the same kinetic energy. And we'll often use the root mean squared velocity, which is a special type of average, instead of average velocity. So root mean squared velocity, I'm not 100% sure if this is u or if this is the Greek letter mu, but it's one of those. You can just call it u, I don't really care. The root mean square velocity of a collection of gas particles is proportional to the square root of the temperature. So velocity is proportional to the square root of the temperature. So if you increase the temperature, the velocity also goes up, but it's not a 1-to-1 ratio. The temperature is a square root, and that's the Kelvin temperature. It's also inversely proportional to the molar mass of the particles. So it's inversely proportional to molar mass. What that means is heavier particles are slower. Lighter particles are faster, which we've been talking about. And root mean square velocity is described by this equation. The square root of 3 times r, where r is 8.314 joules per mole Kelvin. This is the same r that we've seen before. It's just with different units. So it's joules per mole Kelvin instead of liters atmospheres per mole Kelvin. And then that R value, this new R value, that's the same R value, just different units, right? It's multiplied by the temperature in kelvins. We're working with a gas, and so we are working with temperature in kelvins. This is always the case. And then capital M here is our molar mass, and the molar mass here is kilograms per mole. Which is not what we would typically expect. Kilograms per mole, not grams per mole. We always have been doing things in grams per mole. For the sake of the root mean square velocity, it's much more convenient to do it as kilograms per mole for reasons that we'll see. In our example that we go over in a little bit. Do we have questions so far? The math only gets more fun from here. Maybe with quotation marks around it. Okay, and we've got some graphs. So the graph that we're looking at here is velocity distribution with respect to molar mass. So we've got on the x-axis our molecular velocity, the speed of our particles in meters per second. So we're going from not moving all the way on the left side to moving really, really fast on the right side. And on the y-axis, our vertical, this is our number of particles with that velocity. So if you see a high value, we've got a lot of particles at that speed. If you see a low value, we don't have very many particles at that speed. So we're looking at a distribution. Where are most of the particles moving at what speed? And we've got this for a couple of gases. So for O2, N2, water, helium, and hydrogen gas. So for our oxygen gas, we can see that our peak is way back here. And if we were looking at the area under the curve, most of our particles are going to be moving at this slow speed, somewhere below 500 meters per second, with the majority of our particles moving at whatever this peak is at. If we go to nitrogen gas, nitrogen's a little bit lighter than oxygen. Our distribution has shifted over to the right. So instead of all being clumped up over here in this under 500, it's shifted over a little bit more, and we can see that the front tail is also crept out a little bit. So we've got a wider distribution. When we move to H2O, our peak shifts over a little bit more and spreads out. And when we get to really light stuff like helium and hydrogen, our curve starts to flatten out considerably, and our peak has also shifted over quite a bit. So what this is saying is that on average, for example, hydrogen gas particles on average are moving way faster than our oxygen gas particles, even though they're at the same temperature, so they've got the same kinetic energy. Because they're a lighter particle, they're moving a lot faster. We're still going to have some particles that move really slowly, but on the whole, the average, which we could just think of as the peak, the average is going to be much, much higher. So generally, they're going to be moving a lot faster. We can also look at one gas and how its velocity distribution or its speed distribution changes with temperature. So we've got velocity distribution as a function of temperature. We're looking at different temperatures. So we've got, again, molecular velocity, the speed of our particles on the x-axis. And now we've got nitrogen particles, nitrogen molecules, and the number at that velocity. So it's a similar sort of thing, but now we're just looking at nitrogen, and we're looking at a couple of different temperature situations. So at 273 Kelvin, so freezing point, roughly, of water, most of our particles are moving slowly, maybe in this like 300 meters per second range, just based on where our peak is. We do still have some particles that are going over 1,000 meters per second, but for the most part, they're going much slower than that. If we increase the temperature to 1,000 Kelvin, which is really hot, or 2,000 Kelvin, we can see that our average velocity increases quite a bit. And it also spreads out. So our peak isn't quite as sharp. It's a little bit wider, a little bit more spread out. So we've got a wider range of velocities as we increase our temperature. We're still going to have some that move really slow, but for the most part, our temperature and our velocity are both increasing. So we've got a lot more particles at these higher speeds, and we've got some at these very, very high speeds as well. And this is kind of happening. We're just looking at a couple of instances, but you could imagine that if we go from this really sharp peak at 273 and we were to gradually increase the temperature, you would just see it kind of spreading out, flattening out, and that curve just generally moving towards the higher velocity. I just don't have a graphic that shows that. I'm sure that there's somebody on YouTube with one. So temperature increases, generally velocity increases. The distribution is also going to spread out. That peak is kind of flattening, and we've got a wider range of velocities, some really slow particles and a lot more really fast particles. Questions about either of those graphs? You don't really need to know, like you wouldn't necessarily have to be able to draw a graph with great accuracy or precision, but you should generally understand the principle of them spreading out and the distribution shifting higher with either mass or temperature. Okay, root mean squared velocity. Calculate the root mean squared velocity of a gaseous xenon atoms at 25 degrees Celsius. We would need to know what our root mean square velocity is. So I'm guessing that it's mu RMS equals square root, and we saw 3 RT over M, where R was equal to 8.314 joules per mole Kelvin. Temperature is in Kelvin, and big M was molar mass in kilograms per mole. I think the math here is relatively simple and straightforward. I would like you, though, so that you've got some practice working with it, do the calculation, see what you come up with. All right, so really the only difficult part, I think, about doing this problem is there's a couple of places where you could screw up. Not putting it into your calculator correctly, particularly with regards to the square root function. And then the other area is units. Units are most likely where you're going to get screwed up. We are maybe not expecting to use the R value that we're using, the 8.314 joules per mole Kelvin. You're probably also, you wouldn't, if you were just looking at this without having any context, you probably also wouldn't expect that the molar mass is going to be in kilograms per mole. It's important that they are in these units, though, that they're in joules per mole Kelvin, and that it's in kilograms per mole, so that our units work out correctly. There's a mnemonic device for remembering this value of pi, or this value of R, and it's I8 pi. 8 like the number 8, and then pi like 3.14, so 8.314 I8 pi. I've heard that that's helpful for some people, so there you go, if that helps you. As far as remembering that the molar mass is in kilograms per mole, you just have to know it. Okay, so we were working with gaseous xenon atoms, and they are at 25 degrees Celsius. Since we are using a gas, we're working with a gas, we need this 25 degrees Celsius to be in Kelvin. So we're going to add 273.15, and we'll get 298.15 Kelvin. Our M value for xenon, our molar mass is 131.29 grams per mole. Converting the grams to kilograms, we just divide by 1,000. So 0.1 0.13129 kilograms per mole. So putting that all together, for our root mean squared velocity, we've got the square root. 3 is one of our integral numbers. It's part of the equation. And then I8 pi with units of joules per mole Kelvin times our temperature, 298.15 Kelvin. And then our molar mass is 0.13129 kilograms per mole. So for our units, you can hopefully see we've got kelvins and kelvins. One of these is on top respective to the other, relative to the other. So those will cancel out. And then in the top part, the numerator, we've got a moles that's in the denominator. In the bottom part, we've got a moles that's in the denominator. Those will also cancel out. This moles up top is secretly on the bottom. This moles on the bottom is secretly on the top, just because they're the way that they flip, they inverse. So then the units that are left are joules and kilograms. I'm going to plug these numbers in just so that we can get one number, and then we can work out the units after that. So 3 times 8.314 times 298.15. So multiplying everything that's on the top, and then dividing by 0.13129. So we get 56641.4 and some other stuff still in the square root function. And then we've got joules over kilograms. And this is where this helpful little note comes in. 1 joule is equal to kilogram meter squared per second squared. So let's plug in kilogram meter squared per second squared. When we do that, we can see, hopefully, that our kilograms are going to cancel out. And that's why it's very important that our molar mass is in kilograms per mole. It's so that the kilograms here cancel out when we substitute in for joules. So our kilograms cancel, and then the units that we're left with are meters squared per second squared. Any questions so far? Okay, and then we do the square root function. So we'll square root our answer. The number that we get out is 237.99, which all rounds to 238. And when we take the square root of meters squared per second squared, it gets rid of the squared parts. And so we're left with meters per second, which is units that we would maybe identify as velocity. It's a unit of length over a unit of time, like miles per hour, for example. So the kilograms per mole is important so that our units cancel out. If you are doing the square root, if you do the calculation inside first and then square root it, you shouldn't have any issues. Otherwise, just make sure that everything on the inside is within parentheses so that it all gets hit by the square root function. All right, we've got some particles in a box. 3 situations. Which sample of an ideal gas has the greatest pressure? We want to assume that the mass of the particle is proportional to its size and that all the gas samples are at the same temperature. So same size box, they're at the same temperature, and the size, the mass of the particle is proportional to its size. So in B, these big balls are going to be much more massive than in A or C, where we've got the smaller particles. There's one that we can rule out, I think, pretty quickly. Does anyone know which one that is? A. We can rule out A. We can rule out A because the number of particles, it's got 7 particles. B also has 7 particles, but B has bigger particles. So B has more massive particles. So B is going to have higher pressure because it's going to have more kinetic energy. I think that's accurate. We can also rule it out relative to C because C has more particles. And now I need a second to think. Okay, the instinct is to rule out A because with B we've got more massive particles. I'm not entirely sure that it makes a difference. I'm pretty sure it doesn't make a difference. If I was less tired, I think I would have the answer more quickly. The reason that the size of the particles shouldn't matter, I think, is because of our root mean squared velocity. So the mass and the temperature, the way that it all plays out with like these graphs. We're at one temperature value, so we're going to have a different range of velocities, but the kinetic energy should be the same for the particles. So A and B, because they have the same number of particles, should have the same kinetic energy. So I think they should have the same pressure. So the only one that's different really is C because it has more particles. And since we have more particles, we've got more pressure. You could check in your book Conceptual Connection 6.8, and I'm guessing that'll be the same answer. So it's C because we've got more particles. But because they're all at the same temperature, not at the same velocity, since they're at the same temperature, A and B are actually the same. So that's fun. What else is fun is mean free path. And mean free path, mean here we're talking about an average. You may remember that mean is also another way of saying average. It's a specific type of average, I think, but that's not important to us. So the mean free path is the average free path, and the free path is just how far you can go without running into something. So in a gas, our particles are traveling in straight lines until they hit something, and then they get deflected, and then they travel in a different straight line until they hit something else, and then they travel in a different straight line. And we've got that represented sort of by this red particle here, so we can see either where it came from or where it's going. Presumably it's where it's going. So it came in from this red line, it hit off a particle, it bounced, it hit off another particle, it hit off another particle, and it just continues in a straight line until it runs into a particle. And it's going to be making tons of collisions, and it's going to be changing direction a ton, but we can calculate, which is crazy, it's crazy that we can calculate this, we can calculate the average distance that the particle will travel until it collides into another particle. And that's the mean free path. So the mean free path, the average distance a molecule travels between collisions. Our mean free path, the amount of distance that you can travel before you run into something, is going to decrease if you increase pressure. Because if we're increasing pressure, you can think of that as either adding more particles in, so there's going to be more particles, and so you're more likely to run into something. Think of just driving like a maniac on a highway. If it's busy, there's a good chance that you'll run into somebody. If there's nobody on the road, you're not going to run into anybody, right? And it's the same way for particles. If there's nobody on the road, if it's COVID times, everybody's at home, you can drive like a maniac and you're probably not going to run into anybody because there's nobody to run into. If nitrogen molecules were the size of a golf ball, then it would travel about 40 feet between collisions, which is maybe like the length of the room. I think the length of the room is a little bit longer than that. So it's a relatively long distance. And I don't think that we calculate mean free path, but it is something that can be calculated. Which again, I think is like wild. You can look up the formula if you're interested in calculating mean free path. But that's just the general idea. We've also got some similar looking words, diffusion and effusion, which are also gas related words. So the way that gas molecules spread out from high concentration to low concentration is called diffusion. Diffusion, we can generally just think of being as spreading out. I think this is also used in like perfumes or other scented things like candles or scented essential oils. Like if you've got a little container and you've got the like wooden stick things in it, that's a diffuser. You're taking the concentrated scent smells in the little glass vase or whatever it is, and you're spreading them out. So you're going from a high concentration, spreading it out into the rest of the room where there's presumably none of the scent initially. So you're spreading the smell out throughout the room. And gas particles also move in this way, moving from a high concentration to a low concentration. That's generally the way that things spread out. Heavier particles are going to diffuse more slowly because they move more slowly. At a given temperature. So at a given temperature, heavy particles are going to spread out more slowly because they've got the same average kinetic energy. Light particles move really fast, and so they're going to spread out more quickly. And then we've got a related process called effusion. And this is just the process by which a gas escapes through a small hole into a vacuum, which feels like a very particular word, an unnecessarily particular word. So if you have a box and you've got a little hole in the side, and on the other side of the hole is a vacuum, there's no particles, effusion is how quickly those particles will move through that hole. And these are both related to root mean square velocity, which remember is this mu RMS that we calculated previously. For gases at the same temperature means that they're going to have the same kinetic energy. The rate of gas movement is inversely proportional to the square root of molar mass. That's one of the properties of this mu RMS. So the rate of gas movement inversely proportional to the square root of its molar mass. So high molar mass low rate of gas movement is basically what that second point is saying. Because the high molar mass particles are going to move more slowly. Okay, so Graham's law of effusion. This is that scenario that I was describing to you. We can do calculations with Graham's law of effusion. So we've got a box here on the left where we've got gas particles. We've got a box here on the right where initially we have a vacuum. There's no particles in here. There's no pressure. And we've got a little hole that the gas can escape through. So if we've got two different gases at the same temperature, the ratio of their rates of effusion, the ratio of the rate that they travel through this hole, is related by this following equation. So the ratio of the rate of gas A to gas B is the same as the square root of the molar mass of B over the molar mass of A. So on one side A is on top, the other B is on top. A is on the bottom. Helium, for example, is going to escape from balloons faster than air because the smaller helium atoms move faster, they effuse faster than N2 molecules. So if you were to fill up a balloon with helium, you were to fill up a balloon with just air is mostly nitrogen, and the helium balloon, because the helium particles are smaller and balloons actually have little holes in them, the helium balloon is going to deflate faster. They're going to escape the balloon faster than on the air molecule side. So we can calculate the ratio of the effusion rate. We're not calculating the effusion rate, just the ratio of the rate, how much more rapidly one effuses, of hydrogen gas to krypton gas. So we're using rate A over rate B equals square root molar mass B over molar mass of A. And it's not important that we use kilograms per mole or grams per mole for our molar masses, since we're doing molar mass divided by molar mass. As long as they're the same units, it'll work out. So go ahead and give this one a try. All right, relatively simple calculation. Again, the important thing, we want to make sure that when we apply this square root, we're doing it appropriately. We're getting both of the terms captured. The other thing that we need to be mindful of is what we're identifying as A and what we're identifying as B. So let's call A hydrogen gas. And let's call B krypton gas. What's the chemical formula for krypton gas? What's the chemical symbol for krypton? Kr. Krypton is one of our noble gases. Our noble gases all just exist by themselves because they're perfectly content to be by themselves. Hydrogen gas, hydrogen is H. What's our hydrogen gas formula? H2. So it's the other part of the reason that I gave you this as a thing to try, because it's H2, it's not just hydrogen. You may remember H7, so hydrogen plus nitrogen to fluorine and then down to iodine, or horse's knee oats for clear brown eyes, or Brinkelhoff, or whatever other method you decide to use to remember our diatomic gases or elements. So we'll get our molar masses. The molar mass for our hydrogen gas, 2.016 grams per mole. And for krypton, it's going to be 83.80 grams per mole. So the rate of the hydrogen gas over the rate of the krypton gas, this is their effusion rates, is equal to 83.80 grams per mole over 2.016 grams per mole. When we do that division, the grams per moles cancel out. So we will do square root of 83.8 divided by 2.016. And we get a value of 6.4. We'll round it to 3 sig figs just for no real reason. It's just a nice number. So it's 6.45. So what this means, this 6.45, means that hydrogen gas, H2, is going to effuse 6.45 times faster than krypton gas. So it'll escape through a small hole into a vacuum almost 6.5 times faster than krypton gas. Questions about either of our examples or slides so far? Cool. We also, as I've alluded to, we live in a real world. And in our real world, we've got real gases. We don't have ideal gases, unfortunately. We've been working in the ideal gas world, but there are some limitations, there are some exceptions, there are some problems with ideal gas rules that they don't apply perfectly to our real world gases. So an ideal gas, for example, has no attractions between gas particles. Real gases do have attractions between gas particles. An ideal gas also has a negligible, aka zero, particle volume. So our particle volume is as small as could be possible. In the real world, our gases do actually take up a little bit of space. It's not a lot of space, they're still very small particles, but they do take up some space. And so with both of these, we can actually run into some issues. Our real gases are very similar to ideal gases if we're at STP or if we're close to STP. So if we look at the molar volume of a couple of different gases, for an ideal gas, it's going to be 22.41 liters. That's something we've seen before. If we look at a couple of other gases like chlorine, CO2, ammonia, nitrogen, etc., you can see that all of these values are relatively close to 22.41 liters. The one that's most different is chlorine at 22.06, which is a relatively small difference compared to our ideal gas. However, this is again at STP, so we're talking about standard temperature and pressure, 0 degrees Celsius, and 1 atmosphere of pressure, which is relatively low pressure and relatively high temperature, depending on your context. If we change some of those properties, if we deviate from STP and we look at some of the edge cases, like high pressure. If we're at low pressure, the molar volume of argon is nearly identical to an ideal gas. So it works fairly ideally. If we increase the pressure, like by decreasing the volume of a cylinder, so if we take this gas and we compress it down into a smaller and smaller space, that'll increase the pressure, and the particles are getting closer to each other. And because they're getting closer to each other, we're taking out a lot of that negative space, that zero space, that empty space. And so now the particles are taking up a considerable amount of the space, or at least more of the space than before. And so the size of the particles now actually matters here. So particles take up more relatively space, more space relatively, compared to the frame on the left, where there's a lot of empty space, and so we can mostly ignore the volume of the gas particles. So because real molecules take up space, the molar volume, the size of the gas, is larger than predicted at high pressure. So we've got a graph. We've got pressure on the x-axis, so as we're moving left to right, we're increasing the pressure from 0 atmospheres to a staggering 1,200 atmospheres. Again, we live at 1 atmosphere, so we're like basically at the y-axis here. And then our molar volume, we've got on the y-axis. So we've got taking up no space here at the bottom and having a large volume up here at the top. And we can see that if we're at relatively low, compared to the graph, relatively low pressure, our ideal gas in red and our argon gas are the same. As we increase the pressure, as we push those particles closer and closer together, their size starts to matter more. And so argon actually takes up a larger volume than we would expect because of the size of the gas particles. So we really cram them together. The gas particle, the size of the particles actually matters more, and it's taking up space. And because it takes up space, that's adding to the molar volume of the gas. The size of the particle is making a significant contribution to the size of the gas. So size matters at high pressure. The volume of a real gas is higher at high pressure. Again, if we're at low pressure, the size of the gas particles doesn't really matter. It doesn't make a meaningful impact. And so it's basically the same as ideal. This is one of our 2 cases where we can deviate from ideal gases that we'll talk about. There's probably a lot of other ways that we won't talk about. In 1873, Johannes van der Waals modified the ideal gas equation to fit the behavior of real gases at high pressure by accounting for molecular volumes. This was a long time ago, but he said he came up with this equation, V equals nRT over P. Notice that this looks very similar to PV equals nRT. So this is our ideal gas law part. And then there's a correction factor added. So this correction factor takes into account the size of the particles. So we're adding a little bit of volume on, and it's related to the number of moles, which is N, and B, which is called the van der Waals constant. And there's a different van der Waals constant for each gas because the particles of each gas are going to be slightly different in size. So normally if you're doing this, somebody has probably already calculated the van der Waals constant for the gas or hypothesized about it at least. And so you would just look it up or get it from a table. B is not the only van der Waals constant. There's another force that comes into play. So if we're at high temperature, like we are at now, relatively high temperature, the pressure of the gas is nearly identical to that of an ideal gas. There's no pressure deviation or difference. This is because we've got high kinetic energy at high pressure, high temperature, sorry. High kinetic energy at high temperature. Our particles have a lot of energy, and so when they're colliding with each other, they have a lot of energy, and so they're going to bounce off very quickly. So they're relatively weak intermolecular attractions because they're a little bit sticky, but they're hitting each other very, very hard, very quickly. They're moving and bouncing off very fast. So the intermolecular forces are negligible at high temperature. You could sort of think of if you put like double-sided sticky tape on like 2 cars and you had them like bump into each other at just the perfect time that the double-sided sticky tape touched both of the cars. if they're driving at 60 miles an hour, it's not going to make any difference. Or if you have like giant pieces of Velcro on the sides of two cars and they're like driving into each other and they bounce off on the Velcro, like the Velcro is going to have an effect, but they're cars, they're big cars, they're traveling really fast. It's not going to have really any attractive force at all. Versus if you covered yourself in, you know, the hook part of Velcro and somebody else in the loop part of Velcro, and you just like walked into each other, you would probably get stuck together because that's a lot of Velcro if you're all covered in Velcro. So at low temperatures, the pressure of the gas is less than that of an ideal gas because of that stickiness, that Velcro force, or that double-sided sticky tape force. So the collisions lose energy from attractive forces. That Velcro is causing the particles to stick a little bit and slow down. And so the pressure that we would expect to see with no slowing down from collisions, that pressure is lower than we would expect. So the pressure is lower than an ideal gas. And van der Waals also accounted for this. So van der Waals also has an A constant. We saw the B constant on the previous slides. And so we've got now our ideal gas law with P isolated. So our ideal gas law part over here. And then the correction factor is A times the number of moles divided by the volume. And again, A is a value that you would look up or get from a table. And we've got a graph, so we've got temperature here on the x-axis, we've got pressure here on the y-axis, and we can see that at really high temperature, like over 1,000 Kelvin, our two lines for our xenon and our ideal gas are the same. We're seeing ideal behavior from our xenon relative to an ideal gas. If we lower the temperature, if we decrease the speed of the particles, the kinetic energy of the particles, now they're not colliding as forcefully, and so the little bit of stickiness, the little bit of attractiveness that they have for other particles starts to become important. It starts to slow down their collisions and make a difference. And because they're slower collisions, we get a lower pressure. We've got less forceful collisions, less rapid particle speed, so that also decreases pressure. And we can combine both of those equations together. So the way that we do this, if you set both of our van der Waals equations that we looked at with nRT on one side, so you would P plus this A n over V squared, set that over to one side. That's where we get this P term from, and then the V minus NB is from our previous equation. So for our pressure force, or pressure, we've got a correction for intermolecular forces. That's with our A n over V squared. And then for our volume, because our particles do take up space, we also have this correction for particle volume. And they've got very fun units and numbers for them. You basically just need to know how to plug numbers into the equation to use them. I think van der Waals real gas equations are just kind of annoying. And I'm guessing that you'll probably feel the same way. So we can all agree on that. So for real gases, we get to use the van der Waals equation. We can also plot van der Waals equations, or van der Waals real gas forces versus ideal gas forces. So for our behavior of real gases, we've got pressure here on the x-axis in atmospheres. So we're going from low pressure to high pressure. And then we've got our PV over RT over here on the left. For an ideal gas, it's the same behavior across all pressure values. And then we've got some weird shapes for some of our other graphs. If we've got a curve that is lower than ideal, so if it's below, then that means that the most important factor is intermolecular attraction, so they're sticky molecules. So things like water, which has really high intermolecular forces because it has hydrogen bonding. H2O has really strong intermolecular forces, and so we see that it is lower than our ideal gas at all pressures that we're looking at least. For xenon, which is a relatively large noble gas, it's got relatively large dispersion forces or London forces, and so at lower pressures, it's got a lot of importance placed on these intermolecular attractions. Everywhere that it's higher than the curve means that the volume of the gas is a more important factor. So for helium being really small and having relatively low dispersion forces, the size is the more important issue. And so at all pressures, we can see that it's above our ideal gas. And for most of the other ones, it's also above our ideal gas. I probably won't ask a question about like interpreting this graph, because I don't think it's that important, but there's a decent chance that van der Waals might show up, and I'm guessing that it probably shows up in the homework as well. But again, you just need to know how to use the formula, plug stuff in, and then look things up in a table. Any questions about gases? Great, then we'll stop there.